Hello friends, this video on Neet wave optics is brought to you by examfear.com. No more fear from exam. Question number 14. Assertion. To observe diffraction of light, the size of obstacle or aperture should be of the order of 10 to the power minus 7 meters. Reason, 10 to the power minus 7 meters is the order of wavelength of visible light. Now, many times you are asked this kind of questions on assertion and reasoning. So here, if you think that both these statements are correct and also the reason is the correct reason for the assertion, then you have to mark option A. Right? If you think both are correct but R is not the correct explanation, then it's B. If one A is true and R is false, then it is C. And if both are false, then it is D. Okay, so now let's try to understand the statements first. So the assertion says that to observe diffraction of light, the size of the obstacle or aperture should be of the order of 10 to the power minus 7 meters. Now, it is very important for diffraction that the size of the obstacle or the aperture is approximately equal to the wavelength of visible light. Now, if you quickly remember the diffraction setup of maybe Fraunhofer diffraction, if you just quickly try to remember that this is how your slit width is, and on the screen you see a central maxima, and on either side of the central maxima you have secondary maxima and minima respectively. And if you actually try to look at the width of the slit, let's say that the width of the slit is A, you would see that most of the light is diffracted in the central region. That is, most of the light is diffracted somewhere between the two first order secondary minima. Right? So in the central region itself, which we call as the central maxima. Now it has also been observed that if this is the width of the central maxima, the width is inversely proportional to the width of the slit. So if the slit is very wide, it's like the size of the aperture is very big, in that case the width of the central maxima is very less. So that means the aperture size should not be very big, because if it is very big, in that case your central maxima is very small, so you would hardly see any diffraction taking place. In fact, if you would like to put it in mathematical expressions, you can say that the slit width, which is basically the size of the aperture A, is inversely proportional to theta, where theta is the angular divergence. If this is theta, so this A is inversely proportional to theta. That's what I was telling just now, that if A is very small, like the slit is very small, in that case this theta is quite big, so you actually have a very big wide central maxima. Whereas if this A is very big, that means if the width of the slit is huge, in that case this theta is very small. In fact, the theta could also reduce to almost 0, where you do not see any diffraction at all. Right? So if you actually look at, if you look at it from the mathematics perspective, so we have learned that what is the condition for seeing the secondary minima, because the position of the secondary minima decides the width of the central maxima. If this is y, let's say this is y, this is y, so together the width of the central maxima is 2y. So the condition for secondary minima is A sine theta is equal to A lambda, n lambda. So you can say A by lambda is equal to n sine theta. Right? So here, looking at this expression, you see that if the value of A is very large than the wavelength, in that case what would happen? If A is very large, in that case the theta might be very small. So theta might be so small that it might be almost near to 0. And when theta is so small, then there would be no diffraction taking place. Right? And do we want that to happen? No, we want to see diffraction. We want diffraction to take place. So that means for diffraction to take place, the value of A should be comparable to the wavelength of light. In fact, it should be comparable to the wavelength of visible light, because visible light is something that we see. Correct? So we can say that A and R both are correct. In fact, R is also the correct explanation of A. So option A would be the right one. Question number 15. Light with an energy flux of 25 into 10 to the power 4 Weber per meter square falls on a perfectly reflecting surface at normal incidence. If the surface area is 15 centimeters square, the average force exerted on the surface is. Okay, so here we are basically talking about some light which is incident on a surface, right? Now it is not incident in this fashion. So basically the light is incident normally on the surface like this. So we have to find out the average force that is exerted. So in this case, in the problem, the energy flux is given. And what is energy flux? So energy flux is actually rate of energy transfer per unit area. So we can say that energy flux is equal to energy per unit area per unit time. Correct? Okay. So now we have to calculate force. And how do we find out force? So force is nothing but change in momentum. So that is force. Correct? So what is the change in momentum in this case? Now when the light is incident on the surface, let's say that the momentum was P. Now when the light gets reflected from the surface, because it is a perfectly reflecting surface, so whatever light falls on it, the entire light gets reflected back as well. So when the light gets reflected back across the same path, so in that case what happens? Again the light has some momentum P, but this time it is in the opposite direction, right? So this time it will have a momentum minus P, because both these momentums would be in the opposite direction. So when you actually try to find out the change in momentum, you would subtract both of these. So the change in momentum would be 2p. So this is the value that we need to find out in this problem. So we have to find out the value of 2p. So how do we find out the momentum? So here we are given the energy. So how is momentum related to energy? So we know that energy is equal to P into C, where P is the momentum and C is the velocity of light. So you can say that force is equal to 2 into E by C. And how much is the energy? So energy will be equal to energy flux into area into time, right? So from this expression we can say energy is equal to energy flux multiplied by area multiplied by time. So how much is the energy flux? It is 25 into 10 to the power 4. And how much is the area? Area is 15 centimeters square, which is 15 into 10 to the power minus 4 meters square, into time, which is 1 second, right? And this divided by C, which is 3 into 10 to the power 8. So 3 5s are 15, and this comes out to be 250 into 10 to the power minus 8, which is equal to 2.5 into 10 to the power minus 6 newtons. So which is the right option? 2.5 into 10 to the power minus 6 newtons. Question number 16. A beam of light of wavelength 600 nanometers from a distant source falls on a single slit 1 millimeter wide, and the resulting diffraction pattern is observed on a screen 2 meters away. The distance between first dark fringes on either side of the central bright fringe is. Okay, just first try to understand the question. So the diffraction pattern always has a central maxima followed by the secondary maxima and minima on either side. Okay, fine. Now in this case, it says that what is the width of the slit? So the width of the slit, which is A, is given as 1 millimeter, and it also says that the screen is located at a distance of 2 meters from the slit. Okay, that's also fine. So we have to find out the distance between the first dark fringes on either side of the central bright fringe. So this is the first dark fringe on this side. This is the first dark fringe on this side. So we basically need to find out this distance. Right? So how do we find out this distance? So let's say that we join this central thing. Okay, so this is the central point. Let's say this distance from the central point is y. So similarly, this distance would also be y. So basically, we need to find out the value of 2y. Correct? So how do we find out y? So this point corresponds to the secondary minima corresponding to n is equal to 1. And what is the condition for secondary minima? The condition is a sine theta is equal to n lambda. So for n is equal to 1, this would be a sine theta is equal to lambda. Now for small values of theta, sine theta can be written as theta. So this would be a theta is equal to lambda. So how can we write theta? So this angle is theta. Now this theta, for small values of theta, theta is equal to tan theta, which is equal to y, that is perpendicular, divided by base, that is capital D. So therefore instead of theta, we can write y divided by capital D, which is equal to lambda. Or we can say y is equal to lambda divided by a into capital D. So that's the value of y. So therefore 2y will be equal to 2 lambda capital D divided by a. Now let's put the values. 2 into lambda, which is 600 into 10 to the power minus 9 meters. Capital D is 2 meters divided by a, which is 1 millimeter, that is 1 into 10 to the power minus 3 meters. So this would be equal to 2400 into 10 to the power minus 6. This is equal to 2.4 into 10 to the power minus 3 meters, or we can write it as 2.4 millimeters. So this is the answer. That's option D.
Thank you. Please visit examfear.com for free quality education. You can learn with a simple 4-step learning process wherein you can watch video lessons, you can ask your questions, you can refer notes, and you can take a free online test. We have content for class 6 to 12 on physics, chemistry, mathematics, and biology along with practical videos. So please subscribe to our channel for daily updates. Thank you.